You know, you're a master of physics every single day, and you probably don't even realize it. Today, we're going to dive into the science of collisions. Yeah, those invisible rules that control everything from catching a ball to, surviving a car crash. We're about to unlock the secrets of momentum and impulse.
But first, I've got a question for you. Think about the last time you jumped off of something, even just a little step. What did you do the second your feet hit the ground? I bet you bent your knees, right? You didn't even have to think about it. So why do we do that? Just keep that question in the back of your mind for a few minutes.
Because believe it or not, that life-saving instinct, the one that makes you bend your knees, it's run by the exact same principle of physics that powers a life-saving invention, the airbag. How is that possible? How can our own biology and our smartest engineering share the very same secret?
Well, the answer to this whole mystery gets unlocked when you understand two really powerful ideas: momentum and impulse. And I promise, by the end of this, you are going to see exactly how these two things connect our instincts to our best inventions.
Okay, let's start with our first clue in this whole investigation, this concept called momentum. The easiest way to think about it, it's kind of the measure of an object's unstoppability. So, what is momentum really? Well, the physics definition is pretty simple. It's just an object's mass multiplied by its velocity. I love thinking about it as just mass in motion. That's it. The more mass something has, or the faster it's going, the more momentum it's packing.
And the formula? It could not be simpler. P is what we use for momentum, M is mass, and V is velocity. It's a really direct relationship. You double the mass, you double the momentum. You double the velocity, guess what? You double the momentum.
So, the takeaway here is super simple. If you want to make something really, really hard to stop, you either need to give it a ton of mass, a ton of velocity, or, for that maximum get-out-of-my-way force, a whole lot of both. And this image just illustrates the point perfectly. I mean, look at it. A freight train has an absolutely enormous mass, and when it gets moving, its velocity is also pretty significant. You combine those two, and it has a staggering amount of momentum. This is exactly why a train can take over a mile to come to a complete stop. It's just pure physics in action. Okay, so if momentum is the unstoppability, then how in the world do you actually change it? How do you stop it? Let's move on to our second clue, which is what builds on this. Impulse. An impulse, well, it's the real game changer.
Impulse is defined as a force that's applied over a certain amount of time. So while momentum is mass in motion, you can think of impulse as the push over time that you need to actually change that motion. See, it's not just about how hard you push, but for how long you push.
And here it is. This is the secret sauce, the link that ties everything together. It's called the impulse-momentum theorem. It basically says that impulse, that's force multiplied by the change in time, is equal to the change in momentum, mass multiplied by the change in velocity. This one equation, right here, is the key to surviving a crash.
All right, we have our two clues. We've got momentum and we've got impulse. Now it's time to put them together and solve the mystery of the airbag and our bent knees. This is going to be the aha moment. So, to see the magic, let's just do a little bit of algebra and rearrange our equation. If we want to understand the force of an impact, which is what we really care about, we can solve for F. So force equals the change in momentum divided by the change in time. Now we can see what's really going on. Okay, let's think about a crash. Your mass, m, that's not going to change. And your change in velocity, delta v, that's fixed too. You're going from, say, 60 miles an hour to a dead stop, 0. That means the whole top part of that fraction, your total change in momentum, is a constant number. It is what it is. So the only thing in this whole equation that we have any control over is that little variable on the bottom, time.
So here's the crucial point, the whole secret. Since time is on the bottom of the fraction, they have an inverse relationship. To make the force of the impact smaller, you have to make the time of the impact longer. That right there, that's the secret to cushioning.
And that brings us right back to the airbag. An airbag does not reduce the total change in your momentum. You still have to go from 60 to 0. But what it does, so brilliantly, is it increases the time it takes for that change to happen. By spreading that impact out over a few extra milliseconds, it drastically reduces the peak force on your body. And it's the same thing with bending your knees. You increase the time it takes to stop, which reduces the jarring force on your joints. It is the same beautiful physics.
So, we've basically cracked the code on how to survive a collision. But that's really only half the story. The outcome of a collision also really depends on what happens to all the energy involved. So let's take a look at the different ways objects can collide.
Okay, here's the one golden rule. In any collision where there are no outside forces messing with it, what a physicist would call an isolated system, the total momentum before the crash is always equal to the total momentum after the crash. Always. It might get passed around between objects, but the total amount in the system never, ever changes.
Okay, got it. Momentum is always conserved. But what about the energy? Specifically the kinetic energy. You know, the energy of motion. Does that stay the same too? Well, the answer to this question is what separates the different types of collisions from each other. And this brings us to the two main categories. You've got elastic collisions and inelastic collisions. Now, look, in both of them, momentum is conserved. That rule never breaks. But the key difference is kinetic energy. In a perfectly elastic collision, the kinetic energy is also conserved. The objects just bounce off each other perfectly. But in an inelastic collision, some of that kinetic energy gets lost. It turns into heat or sound, and the objects might get bent out of shape or even stick together.
The classic textbook example of a nearly perfect elastic collision is a Newton's cradle. You lift one ball, let it go, and one ball flies out the other side. The momentum and the kinetic energy are just transferred almost perfectly right through the chain.
But here's a really good question. If one ball with a certain mass and velocity hits the line, why don't two balls fly out the other side at half the speed? I mean, think about it. The total momentum would be the same. The math works out for momentum. So why doesn't that ever happen?
And the answer is all in the energy. Because while that two-ball scenario does conserve momentum, it completely fails the second test for an elastic collision. If you actually run the numbers for the kinetic energy, that scenario somehow loses half of the initial energy. And since a Newton's cradle is built to be elastic, that's just impossible. You can't just lose energy like that. The only outcome that follows both rules, conserving momentum and conserving energy, is the one we actually see in real life. One ball in, one ball out.
So in the end, physics isn't just a bunch of formulas on a chalkboard. It's like the invisible script that's running the whole universe. From the way you land after a little hop, to the safety features in your car, all the way out to the way entire galaxies collide. So the next time you see a collision, any collision at all, what are you going to see differently now that you know the script?